Assalamu alaikum, everyone. I welcome you all on behalf of OWASP Riyadh, and we are honored to host Mr. Khalid, who will be speaking on the challenges and opportunities in TLS 1.3 monitoring. And Khalid is already here. So before we start, we'll just give a brief introduction about Khalid. So Khalid Al-Suhail is a senior incident response consultant with IBM X-Force IR team, and he holds the prestigious SANS GX certifications like GDAT, GCIH, and also Certified Threat Hunting Professional, and along with a couple of other certifications. And he is a fierce forensicator who understands how the adversary thinks and what they might do. Also, he is a known speaker on digital forensics incident response, and he has spoken at RSA Abu Dhabi and as well as International Cybersecurity Conference in Riyadh. And today we are honored to host him, and I welcome you all. And I invite Khalid to please start his presentation. So,
Assalamu alaikum. Thank you very much, Brother Atif. Assalamu alaikum wa rahmatullahi wa barakatuh, everyone. Thank you very much for attending today. I know Saturday is not the best day for talks like that, but fortunately, this is what that was already scheduled. Just to confirm that you all can see the slides right now, right?
yes, your slides are visible. Your slide is visible.
All right, so just to add up to what Atif said, I am an incident response consultant, part of the X-Force IR team. And within my X-Force IR team, I'm responsible for both IR and proactive services within the EMEA region. By proactive services, that includes threat hunting, compromise assessment, and this is our topic today lies within the scope of these proactive services. Prior to IBM, I worked in both the Technology Control Company in Riyadh and the National Cybersecurity Center, in which I spent most of the time doing in digital forensics and incident response. Besides my job duties, I'm also interested in advanced threat analysis and host and network threat hunting. Now, topic that I will be talking today is a TLS 1.3. TLS 1.3 is not yet fully adopted by everyone. However, currently the speed of adoption is actually much faster than anyone thought. And with the introduction of TLS 1.3, there will be a lot of challenges within the network security monitoring, within the security operation centers. And today I will try to illustrate and show these challenges and the impact that they might have on our current technology used, such as IDS, IBS, or proxies that we use to intercept and analyze and detect attacks that are encrypted by SSL or TLS. Now, before we get into the TLS 1.3 topic, I like this table because it illustrates how much of a difference happened between TLS 1.2 and TLS 1.3. Before that, SSL 2.0 was first developed and used in-house, and it contains a lot of vulnerabilities. Same thing goes with SSL 3.1, TLS 1.0, and TLS 1.1. Those four protocols are fully deprecated right now. They're extremely vulnerable, and if anyone is using any of these four protocols, then they probably should be, instead of using these protocols, they should use plain text because they're extremely useless. What is currently used is only TLS 1.2 and TLS 1.3. Anything before TLS 1.2 is deprecated. Now, what you first noticed between the difference between TLS 1.2 and TLS 1.3 is how many algorithms are not used anymore in TLS 1.3. What you notice that all the algorithms that are adopted by TLS 1.3 has the word forward secrecy in it. Now you can see in the third line, DHE RSA, which is Diffie-Hellman RSA, the fifth line, EC, which is elliptic curve, Diffie-Hellman RSA, and list goes on, but all of them contains the word forward secrecy. Then that's one of the challenges that TLS 1.3 added to the table. Now, there's one thing very important that I would like to mention, which is what was the main reason TLS 1.2 implemented and what was the main reason of TLS 1.3. TLS 1.2 was introduced, was adopted by, for the purpose of keeping information secure as in encrypted. So if you use your credit card, if you use any sensitive information and you would like this information to be encrypted, in order to make sure no one will steal your information, that's why TLS 1.2 used. So TLS 1.2 was introduced for the purpose of encryption. TLS 1.3 got introduced, but the main purpose of TLS 1.3 is not just encryption, it is encryption and privacy. So within TLS 1.2, an attacker might not be able to know what exactly is your credit card number, but they will know exactly that you're browsing Amazon or you're browsing eBay or you're Googling. What are you Googling? The attacker will not be able to know that. Not just the attacker, anyone inspecting your traffic. Within TLS 1.2, they know where are you going, but they have no idea what are you doing. However, in TLS 1.3, they don't know where are you going. And of course, they have no idea what are you doing. So you will see connections. And is he going to Google? Is he going to eBay? Is he going to GitHub? No one will know that. So in TLS 1.3, it added the privacy, which was extremely missing from TLS 1.2. Now, when we say SSL inspection within TLS 1.2, and how does that happen? In TLS 1.2, usually you have a certificate that is installed in the endpoint, and within your firewall or your proxy, what your proxy will do, it's going to terminate the SSL or the TLS session using the certificate that is installed in the endpoint, and it's going to initiate another connection with the server. So there will be two negotiation happening, two TLS handshake happening between these two hosts, one between the firewall or the proxy and the endpoint, and the other one between the firewall and the web server. So this is the current situation in TLS 1.2. When we added perfect forward secrecy basically eliminated that. The way perfect forward secrecy means, it basically means that even if someone has the private keys, if you have the private and the public keys that are used for encryption, you still will not able to decrypt the entire traffic. And the idea of perfect forward secrecy, it is very simple. Within every session that are created, there is a new private and public keys, not a certificate. It's just a random number that is used to generate a new master key, a new encryption key within every session. So even if someone was able to get a private and the public keys, they will able to decrypt only single session. However, they need the entire keys for both the public and the private. Now, within Windows operating system, these keys are stored in memory and they're immediately wiped and removed from the memory by the operating system. So in theory, these keys will never be stolen unless you have a kernel driver inspecting the memory and capturing every single private and public key. And by key, I mean the random number that is used by RSA to create the session in order to create a master key. Now, attackers, in order to use that, in order to enforce usage of TLS 1.3, in order to enforce the usage of perfect forward security, what they will do is very simple. They basically, within their C2 server, they will only accept TLS 1.3. And by doing that, their malware or the backdoor that is running on the infected system will try to communicate back to the server, and by doing that, the server will only accept 1.3. Anything below 1.3 will be denied. And the main goal of doing that, just to make sure 100% that none of the firewall or the IDS or the IBS or the proxy will be able to inspect what is going on inside that package. Now, the second topic, but before we get to the second topic, I would like to demonstrate how a malware can, how the proxy can decrypt TLS 1.2 and what will happen if you force the server to only use 1.3. If you can give me a second, I'm going to share my VM. I can't find it. So just like for confirmation, you see VMware Workstation right now, right? Do you see both the Ubuntu VM?
Yes, we can see.
Okay.
Yeah.
So now imagine that is your attacker C2 server, and the attacker is using an Nginx. Let's assume that is using Nginx to deliver a second stage malware. Now, what the attacker can do is basically within the accepted protocols for Nginx, it will only accept TLS 1.3. So the default configuration for Nginx is something like that. Within the SSL protocol, it will accept both. This is the default configuration, SSL 1.2 and 1.3, because not all clients support 1.3 yet. But if the attacker already aware that there is SSL inspection within their environments, they will only enforce usage of SSL 1.3 by basically accepting all SSL 1.3 within the Nginx server. Now, if you go back to the VM in here. So what I have in here is BFSense. BFSense is what I'm using as my firewall, and within BFSense, I have multiple services. One of them is the Squid proxy server. So I know this is an open source, but is identical to what you see in most organizations. Within Squid server, you can, of course, enable SSL filtering. Now, by enabling SSL filtering, the only thing that you have to do is within the certificate, let me find it. So within the certificate, I have already downloaded the CA, which is the certificate authority, and I have already installed it on the VM. So basically the SSL inspection that is happening within the Squid proxy server will be inspected by Squid. Now, we can do this two ways. First way is a basic malware. So what you have in here is a small implementation of WinINet API, the Microsoft WinINet API. And within that, I have already accepted the unknown CA, and I have already accepted the security flag wrong usage. So this one should be working if you're using TLS 1.2. However, if you use TLS 1.3, of course, now you can see the IP of the VM, my Nginx VM. And if you manage to execute that, the first thing you're going to get this error. Now, it's very hard to see that error. Let me open up Edge, Microsoft Edge, and let's see what that error looks like. HTTPS. So you see there is an error, and the error was thrown off by the Squid server. It wasn't thrown off by my system. Squid server is complaining, and it says something like the proxy and the remote failed to negotiate a mutually acceptable security setting for handling your requests. Why is that happening? Why can't my proxy, in this case, establish a secure connection to my Nginx command and control server? The main reason, the only reason behind that is basically the perfect forward secrecy. So basically my server will not accept this connection if that connection is coming from my proxy. The malware that is running on my system is the one who should be negotiating the keys with my C2, with none in the middle. Now, if you go within this one again, and let's change it and say, let's accept TLS 1.2 in this case, and let me restart it. So now we have restarted, and if you go back in here and you refresh, see, we got this is the server response, it worked fine. And you can see the certificate in here is lab internal CA. Now, if you come back to the malware, or that stage 1 malware, that should be downloading the second stage by using that. And we can see that it worked fine now. Now, what can you learn from that? This is a very crucial, very important, very interesting use case that you can use to basically detect this kind of malicious uses of TLS 1.3, because there's no, at current stage, any application that only accepts TLS 1.3. TLS 1.2 is still usable. It's not fully deprecated. So if there is a surfer response from the surfer that only accepts TLS 1.3 and will not negotiate anything less than that, then this should be a red flag, and that traffic should be inspected further. Now, let me take a look on that. However, this time, let's take a look at the traffic from the BCAP. So I have restarted that, and I'm going to use TLS 1.3 again. And the same thing in here I will use, but this time, let's get the packet capture. Let's get a BCAP for all the traffic that is going on. So keep it 1, I believe so. And I want any traffic that is going to my C2, the Nginx C2. So let's start it. And in here, let's refresh that. It's complaining. Or do you know what? Let's disable the proxy itself, because that's where you can see the actual negotiation in a better terms. So I have disabled and SSL, so we have no SSL filtering currently. Okay, now let's do that again. So within BFSense, it has, by the way, BFSense is an open source firewall. It does everything that commercial firewalls does. So anything in BFSense, you can do it in your corporate firewall and vice versa. So let's go to the packet capture again and do the same thing, capturing this traffic. Oh, it's already running, my bad. Let's do it again. And let's go there. Okay. Let's see if that captured anything. Cannot connect securely. Yeah, that's fine, because it's self-start certificate of Nginx. So now, because the Nginx certificate is not installed in this server. So let's open up the packet capture within TLS 1.2, TLS 1.3. I'm looking for my TLS 1.3. No. Have we restarted that? 1 second. Yeah. Let's do it again. So I'm going to start this again. So now we can see the traffic is TLS 1.3. Now, from the client hello and the server hello within the BCAP, and keeping that you can build a snort or suricata or any kind of use case to detect this kind of enforcement of SSL 1.3 from the server side. Now, if you go to the supported version in here, you can see that my PC accept TLS 1.2 and TLS 1.3. There is nothing wrong with that. This is the normal behavior, because my server, my workstation accepts both. Now, if you go to the server hello packet and you check the same thing within the server hello, just a second. You can see here the supported version is only TLS 1.3, and this is odd. This is extremely odd. This is extremely abnormal. Even if legitimate usage of TLS 1.3, there's no server or legitimate server in the world that only accepts TLS 1.3 in the moment. So this is the first illustration of an opportunity to detect a malicious usage of TLS 1.3. Keep an eye on any traffic or any server hello from the server side that only accepts TLS 1.3. Okay, now let's go back to the slide. So the second thing that I want to talk about is the handshake. Now, we know that if you have used Zeek or Pro, if you have used Suricata, if you use any IDS or IBS, you know that the majority of the known malwares, we have something called certificates and certificate signature. One of the most famous pen testing frameworks, such as Metasploit, will use a fixed certificate, not a fixed certificate. There's a couple of fields within the certificate that are fixed, so you can detect that this is a Metasploit-like certificate. And now within TLS 1.2, the client will send the hello, the server will send the hello along with the certificate and the signature. So the certificate and the signature in TLS 1.2 is in plain text, and that's why we have many use cases. That's why we have many, let's say, IDS rules that detects malware's known signatures and certificates. Unfortunately, this is not the case in TLS 1.3. In TLS 1.3, you have an encrypted server certificates. So in other words, you will have no idea what is the communication that is happening between them in terms of the certificate itself. So if that certificate is one of the known malicious certificates or signatures that's used by a very known C2 framework, if that is using TLS 1.3, that certificate will be encrypted. Now, of course, there's absolutely nothing you can do at this point. Let me again share my screen, because I want to show you all the outputs of Pro. Again, I'm a big fan of pfSense, and pfSense has a support for Zeek. Zeek is the new name for Pro, which is an IDS or a network security solution. And if you go to the network real-time inspection, if you check the SSL output of Zeek, you will notice something that we have here. For example, let's take these two lines as an example. We have SSL 1.2, SSL 1.3, 1.3, and we have TLS 1.2 in here. What you noticed in here, So notice in here that the field for the SSL 1.3 are completely empty. The issuer, the certificate's name, the chain, everything about the certificate itself, if you're using TLS 1.2 is, TLS 1.3 is encrypted. That is an extreme challenge on any IDS, IBS, or even proxy systems, in order to detect if that certificate is self-signed or that certificate is legitimate. Now, in many organizations, they implement some sort of security controls to prevent any self-certificates, any users from accessing self-certificate. And they do that using the IBS or the firewall or the proxy. Unfortunately, with TLS 1.3, you as the middleman who is inspecting the traffic between the client and the server will not be able to know if that certificate is signed by a trusted CA or if that certificate is a self-signed. You will not be able to know who's the issuer, who's the address, what is the ID of that certificate. So that's just a quick illustration of what I mean by, I'm sorry. Okay, so that's just a quick illustration what we mean by encrypted server certificate. So that is the second challenge in TLS 1.3. The third challenge in TLS 1.3 is something called SNI encryption. Now, within TLS 1.2, SNI, which is the server name identification, was introduced for the main purpose of assume that you have a server that contains 5 or 6 websites. And each one of these websites on the same server, on the same IP, there's 5 websites that are hosted. And for each website of these 5 websites, they have its own private certificates. Now, when your GET request reach the server must be aware which of these 5 websites you're trying to access. And in order to know that, the server will use the server name to figure out which one you're trying to access. And by doing that, it's going to give you the correct private certificate to do the handshake and complete the HTTP communication. that SNI that was used in TLS 1.3 helped a lot of organization to, number one, block connections to known bad domains. For example, if an organization would like to block access to WhatsApp or web WhatsApp, or want to block access to Google Drive or a box or any of these websites, they will always use the domain name to do that. No one will use the IP to block connection to this. And from where can they detect that server name? They will do it, of course, from the server name ID. Now, unfortunately, for security professionals, fortunately for privacy advocates, SNI is now encrypted in TLS 1.3, which can make a building IPS rules extremely hard, because now you have to go back to the old method by instead of using the domain, you will have to use the IP, you have to use the ASN to basically block any connection to the company that you're trying to block it. Now, what is the problem with that? You know that many organizations, many websites currently use services such as Cloudflare. And by using Cloudflare, now the Cloudflare will basically hide the original server IP or the true server IP. So if you have a connection that is going to a Cloudflare server, the connection might be going to anywhere on the internet. You have no idea what is the real host behind that Cloudflare IP. What can you do about that? Honestly, look at China and Russia. What did China and Russia do to prevent that? Well, they basically banned and dropped all HTTPS TLS 1.3 with an encrypted SNI, because at this stage there is no way to monitor this kind of traffic. There's no way to know where is the user going. If that user is using Cloudflare, they could be going to maliciousdomain.com, or they can going to google.com. The only thing you know is the IP where the user is going, and that IP could be in Amazon AWS, it could be on DigitalOcean, it could be on Cloudflare. So there's no way to know where exactly that user is going. This is the three main challenges that I had in my mind. And I think now I'm gonna open the floor for questions.
Thank you very much, Khalid. It was a very good presentation. And we request the attendees, if they have any question, please go ahead. You can either type in the chat box, or you can unmute and ask.
All right, then I think there's no question. Anyway, I believe the majority of the audience have a way to reach out to me. If anyone have any questions, please feel free to reach out to ask.
Okay, great. So, okay, there is one question. Okay, there is a thanks for the presentation, very informative. Okay, great.
Okay.
Let us wait.
Thank you.
Yeah.
Excuse me, guys. Khalid, Jazakallah khair. Thank you so much, man. Wallah, it's a great presentation. By the way, my name is Raed Al-Mtairi. I'm with Atif Khan. We are hosting the OWASP Riyadh here. Khalid, are you going to share the slides?
Yeah, of course.
Either with, so you have like shared it, or you're gonna post it somewhere, or you're gonna give it to us and then we're gonna share it with the audience?
I can share it with Atif, no worries.
Okay, great. Yeah, once you share, we can share it in all our social media accounts.
Sounds good.
Great, thanks.
All right. Thank you very much, everyone. I don't want to keep you long on a Saturday afternoon or Saturday evening. Looking forward to meeting you all maybe in the next talk within OSAP.
Okay, sure. Thank you very much, Khalid. It was,
Thank you so much, man. Allah يجزاك خير.
Okay.
okay, great. Thank you, everyone. And we'll keep you posted about the presentation, our upcoming presentations. Thanks, Khalid, again.
Thank you, brother.
Okay.